Hello, everyone. So in this talk, we're going to look at a few key aspects of Scala that I believe are actually very important for all of us, Scala developers. But before we get started, I actually want to make sure that all of you are able to connect to the internet, because at the end of the talk, we're going to have a quiz. So we're going to have some fun together. We'll see what you learned about the talk. And 3 of you will actually have a chance to win a 3-month Hydra license. So I'll tell you a bit more about Hydra as well. But this talk is not going to be about Hydra. It's only going to be about the vanilla Scala compiler. So who am I? And why am I here talking about Scala compilation? Why do I care about the problem at all? So I've been working on Scala since 2005. So it's been quite a few years now. And all of my Scala professional career has been about Scala tooling. So I've been working on the migration manager, on the scala-italy support, and that also led me to do some work on the Scala compiler just because of the integration between these two components. But about 2 years ago, I founded Triple Quote together with my colleague Julian Dragos. And we've taken on this challenge to make Scala compilation faster. And we have a Scala parallel compiler. And that is called Hydra, and that's how you get to compile Scala faster. But as I said, today it's only going to be about the open source Scala compiler. And this talk is really born from this 2 years experience at Triple Quote, where we've been seeing on the field, on real projects, there are actually very often some easy strategy that you can apply and just get a lot more productive than you are today. So this is what we're going to be looking at today. So first in line is build time is not the same as compilation time. And even though this sounds probably obvious and silly to say, it's actually extremely easy to lose track of what the compile task does in your preferred build tool. So let's have a look at it. Before you start compiling, so when you hit the compile command, whether it's SBT or something else, so on the right you have output from SBT, but that's actually completely irrelevant. The same can happen when you're using Maven or Gradle or something else. When you type compile, you're not actually just going to go and compile right away, but there are other things happening, right? So the first thing that the tool might be doing is dependency resolution. So it needs to be sure that all the dependencies that you have declared in your projects are actually available locally so that they can be used when compiling your program, right? And this can take quite some time, especially in SBT. Even if you have all the dependencies already available to you, just dependency resolution may take several seconds. And in fact, I would highly recommend you to have a look at SBT Coursier. So it's a plugin for SBT. And with that, instead of using Ivy as your dependency manager, you use something else, and it might be a lot faster. So in general, it's a lot faster. Then in the specific, it might depend on your project, but I think it's worth a try. So it's only about adding a plugin to your build and see whether it makes things faster. Then after that, what you may have is source generators. Maybe you're using protocol buffers. Maybe you have some slick table that generates some generator that generates slick tables, right? So Scala code in the end. And those are usually not the fastest things on the planet. Then after that, you may be formatting. So at every time you compile, actually you format your code. I'm not sure that really makes sense during your day-to-day development, but that's something that it's part of your build, and it's usually a good thing, right? And if you look at the output on the right, it's interesting. It says, at some point it says, there is a warning, search state exploded around line 177. So a search explosion definitely cannot be a good thing. And that's a clear indication that time is being spent waiting for the formatting to finish his job. And then on top of all these things, and there are many others, there is also things that are specific to the build tool. So for instance, in SBT, you need to evaluate and build the settings and task graph. And that actually may be slower than you think it is. So it really depends on the project, but maybe like I know an example on the ACA code base, it took something like maybe 30 seconds to just get into the project. So to get into the SBT interactive shell. The SBT team is doing a lot of work to make things better, But those are slowdowns that are important to keep in mind during your day-to-day development. All right, so we're almost ready to start compiling, right? After all these things, SBT is going to use Zinc for compiling your program. So Zinc is pretty much used by all build tools out there in the Scala community. And among the many features it provides, the more important is that it gives you incremental compilation, right? Good, but Zinc will also try to be really smart about what it has to compile. So it will actually go and check basically, it will want to see what are the difference between, well, now and in the past, so that it can actually optimize its work, right? And that's going to take some time. So it needs to build a cache, and that's going to take some time. And on top of that, so it will need to inspect all of your sources and class paths. So in order to build this cache, it will go and actually inspect all your sources and class paths. So there's going to be a lot of input and output. And again, this is going to take time. It doesn't come for free. I actually heard yesterday from John Pretty that the Scala Center is working on some optimization on Bloop so that, well, once this analysis is built, it's actually kept in memory and is not persisted to disk every time. And that's actually what happens today with SBT. So on top of building this cache, it also is persisted to disk and read from disk every time you do, well, not maybe every time, but often enough. For instance, every time you enter inside SBT, well, it has to read this analysis object. And if your project is large enough, if you have a large enough class path, this really adds up. So we're almost ready to compile, right? So now it's the point where Zinc is finally calling on the Scala compiler to compile your sources. Very good. But as we know, Zinc does incremental compilation. So it actually installs 3 additional phases into the compiler pipeline so that it can track the dependencies between the files, and it actually goes at a much lower granularity than that. So that then, whenever there is a change or you make a change, it can find what are, well, what is the set of sources that needs to be recompiled based on those changes that you made, right? Well, this doesn't come for free. So these additional phases that are installed by Zinc are going to have a cost of about 15%. So there is an increase in compilation time around 15% when you compile with Zinc, when compared to the vanilla or the CLI. So running Scala from the CLI, it's actually faster than running it with Zinc for a cold compilation. Of course, the idea or the reason why you're using Zinc is that you believe and you hope that you're going to be profiting, so you're going to get back this 15% time you waited during incremental compilations. So this is basically the contract between you and Zinc. I'm okay to pay a little bit of an extra cost, but I know that during incremental compilation, I'll get much faster because I don't have to recompile everything. And that is true when your sources are loosely coupled. And so Zinc is actually able to do a pretty good job. But reality is that it really depends on the project, and it's not always the case that you have such, nice decoupling between your sources. And there are actually pathological cases where an incremental compilation may take even longer than a full clean build. So it's not a straight it's not a straight answer basically whether we're going to be faster or not with Zinc, but it's something to be aware of. So what is the takeaway from all these things? Well, one thing you should do is definitely use the IDE for compiling your code. Why? Well, the build tool is great for setting up your environment, to fetch all dependencies, to do all these things. You generate the code and everything. But then at that point, you move into the IDE, whether it's IntelliJ or Eclipse or Bloop or something else. And from that point on, you will not be doing any dependency resolution anymore whenever you hit compile. You will not be generating sources every time you hit compile and so on. So as a consequence of that, your development cycle will get to be a lot faster. All right, number 2, type class and macro derivation. So this is a very powerful combination, and it's very widely used in our ecosystem. Lots of libraries out there uses it. An example of this is JSON serialization. So you have some case class, and basically you want to derive some type class so that you can serialize and deserialize those case classes, right? So this is really great, but it's also a ticking bomb. So let's see why. So what happens is that when you derive these type classes, well, one thing you want to be aware of is that you don't derive the same type class over and over every time you use it. Rather, ideally, what you would like to do is derive it once for a specific type and then cache it and reuse it. But in practice, so the reason why you want to do that is because every time there is a type class derivation, well, there is a macro that is being invoked during type checking, and that's going to cost some time. And these things really adds up. So if one macro expansion is really fast, well, if you have 1,000 of them, then it's really going to cost you some time. So this is why you really want to try to cache those type classes instances when they're derived with a macro so that you don't pay this cost over and over. All right, so this works well, as I was saying, but what we have seen in practice is that it's often the case that you have imports that basically generate these type class instances on the spot, right? You have importing your classes so that you don't have to type anything. There is just the import, and then whenever there is a type class of a specific type, like a JSON serializer for a specific type, then that type class is basically generated for you. It's very convenient, right? And we also seen cases where, well, there are those imports, and maybe the type class you need was also added to the companion object. So ideally, so if you know how the implicit resolution algorithm works in Scala, if you put your type class instances in the companion object of the class, the compiler will be able to find that type class instance for you without you having to specify anything. However, if you have the import in scope with the machinery that allows the compiler to generate the same type class, well, the import will have higher precedence over anything you've been putting in the companion object. So basically, even if you have code in the companion object, since you're never calling it explicitly, it will never be used. So effectively, that's that code. And what happens is that your type class is always generated through a macro. And that's bad, of course. But there is additional things for why that is bad. It's not just the time that you're wasting at compiling or type checking and expanding those macros, but it's also that code is being generated out of those type classes that needs to be inserted into your code, right? And this really adds up to your code size. Sorry, it was the next slide. So this really adds up to your code size since this additional code has to not just go through type checking, but also through the old compiler pipeline, since bytecode needs to be emitted for all these additional type class instances that are being generated. But let's make this practical. Let's have a look at an example. So here I have two case classes. One is full name that takes 2 parameters of type strings. And then I have a shipping address that takes 2 parameters of type full name, and then a parameter of type string. Then now let's assume that in our code we need to, the compiler needs to generate a type, two instances of a decoder of shipping address. And assume that you have all the imports, the right imports in place, so the compiler will just do what you ask him to do, and will actually generate the same type class twice, because it will not realize that, once it generated the first type class, the second one is actually identical. So it will not realize that, so it will just generate it twice. And you can see the cost of that generation in the bytecode that is actually emitted for that class. So you can see that every additional type class is going to cost you about 23 kilobytes on top of the compilation time. So there is also a in-memory footprint problem, or the in-memory usage grows because of those additional implicits that needs to be generated. So we can make this a little bit more visual. Say that the Scala compiler, so it needs to find a decoder for shipping address, and assume that, this decoder library is using shapeless underneath to basically look at the case class, at the shipping address case class, and see what are the components that make up this class. So we'll just go on and see, okay, I need actually 2 full names and 1 string. So I need to recursively generate a decoder for full name, well, 2 decoders for full name and 1 for string. And then for full name, it will just go on and do the same, right? So it needs 2 decoders of string as well. And as I mentioned before, it will not realize that the decoder of full name are actually the same, right? So it will just go on and generate 2 of them. And again, the problem is not when you have 2. The problem is when you start having 200s of them or having the same over and over. So what can we learn from this? Well, you really want to avoid regenerating the same type class instance over and over. So the next question would be, okay, how do I do it? So one thing is do not import the type class generator, right? If you don't import them, at least you see an error, and then you can start thinking about, okay, how do I basically cache this type class instance that I need so that I don't regenerate it over and over? And where is the right place to put those type class instances? If you can, put it in the companion object of your case classes. That's the right place because you will not need any import. So you just put it there. The compiler will find the specific type class every time it needs it. You don't always have control over all case classes or class types that exist in your program. So in that case, you might need to put it somewhere else, like in an object or something. But then what you do is importing the object. You don't import the type class generators. You just import the specific implicits that you need in your source file. All right, number 3. This is actually a funny one. So white box macros are type checked 3 times. So you want to be sure, really sure, really, really sure. So let's start by clarifying the difference between a white box macro and a black box macro. So a white box macro is basically allowed to generate new types that can be referred to by the rest of your program. So said in other words, basically the type of the resulting expression after macro expansion can have a more precise type than what it had before. So in the signature. As opposed to that, a black box macro cannot do that. So basically it has to respect the contract. So it cannot refine the type so that you know exactly that the type resulting from expanding the macro will be exactly as it was before. So this is the difference between the two. And so when you have a white box macro, it's all good. Okay, so this is actually a screenshot that comes from the Scala compiler code. And you can see that the first branch, it's how a black box macro is type checked. And it's pretty straightforward. You get the expanded tree of a black box macro, and you just call the type checker once on this tree. And that's about it. While for a white box macro, you can see that actually we go on 3 times. So we type check once, and then on the result of that, we type check again, and so on. So with that, I don't want to imply that a white box macro is 3 times lower at compiling, because of course, a lot of your types and trees a lot of your trees will already be typed after the first time. Symbols will be there. But there is clearly additional work that has to be done for a white box macro. And if you're using libraries that relies on shapeless, so things like maybe Doobie or some components of Circe and other libraries, then I think it's even more important that you realize that you should be caching type class instances that are derived with white box macros, because you're actually paying an even higher cost than with, I would say, standard macros. All right, so I keep talking about type checking and how long it takes to type check. Ideally, type checking should take about 30% of your total compilation time. So when you feel that that's not the case, or when you feel that your compilation time are getting out of your hands, then you should really spend the time to understand why that is the case. And there is actually a compiler flag that is available to you. It's minus verbose. And with that flag, you can see how much time is spent on each of the phases of the Scala compiler to compile your program. So you will basically see type checking, how much time does it take overall compared to the total compilation time. So minus verbose also produce a lot of additional noise. So you'll have to sort of grep to find what you're interested in. But the information is there and available to you, so you can use it. And if you notice that basically type checking, which is the typer phase, takes 80–90% of your time, but probably even less, like 60 or 70, you should really want to know why that is the case. There might be good reasons, and if you're aware that that's normal because I'm using a lot of, I'm deriving a lot of code during type checking, so of course type checking is going to take a lot of time, that's okay. But again, more often than not, those are surprising things. Like one thing that I found out recently is that type checking slick-generated tables can take like 80–90% of the time. So a single source file was taking 80 or 90% of the total compilation time. And that to me was totally unexpected. Again, there wasn't much I could do, but maybe what I can do is actually, if I'm not changing this slick table often, I can actually move it outside of my project, maybe make it a different module or a different component so that I'm not paying the cost of compiling that single file every time, especially on the CI. When you do a full clean build, you always recompile that file, right? So yeah, there are things basically that you want to investigate. You want to realize why compilation is slow, and especially if type checking is involved. It's the reason why compilation is so slow. So the usual suspects for slow compilation are micro-expansion, implicit resolution, and, well, quasi-quotes and type tags. And I would say especially quasi-quotes, you might not realize that they're slow. They are. And if you're rolling out your own macros, I think you should have a look at it. And maybe there are opportunities for not generating, well, for basically reducing the amount of quasi-quotes that you use in the specific class. So I put a couple of flags that I believe are useful if you're actually going into this quest of finding out what are the problems. So once you identify a class where you believe there is a lot of micro-expansion happening, you can use this -x print typer. Yes?
Just want to ask, like, you know the thing that Jorge did with the profiling tool?
I'm going to mention this.
Cool.
Yeah, I'm just going to mention it. Yeah. I'm going to mention it, don't worry. So things that you can do with the vanilla Scala compiler is you can print the tree, so the AST seen by the Scala compiler after typer. And that means that after typer, all macro have been expanded, implicit resolution has happened, so you can basically see the program, how it's going to be, well, compiled down to bytecode, right? And if suddenly you see that, well, you have maybe 30 lines of code and suddenly they become 15,000 lines of code, well, you know that macros are happening in there. And for -x log implicits, that actually tells you what are the implicits that were attempted by the compiler, but they were rejected. So of course, if the compiler is attempting a lot of implicits, there is a lot of time being wasted, which means there are probably too many implicits in the scope that could be a match for the expression that has to be healed. So again, you can use that information to basically reverse engineer the problem, go back to your code, analyze and understand and try to fix your compilation times. And then as Eder was mentioning, I believe starting with 2.12.6, but correct me if I'm wrong, there is a compiler plugin that was developed by Scala Center and Orga in particular that definitely exposes definitely exposes this information and I believe a lot more. The one thing you want to be aware is that it's going to slow down your compilation, so it's not a tool that you should be using as part of your CI, but it's definitely a tool that you should be using whenever you want to understand why there is a compilation problem. And well, since I have a plug about that, I will also say that Hydra actually can provide you those information on a dashboard, so it's a lot easier to consume those information. So there is the open source and then there is the commercial one. Good. So and this is actually related to what we do. So we've been talking a lot about this explosion of the code, and so we came up with a number that actually helps us understand the problem. And we named it the typer parser node factor. And now I'm just going to tell you how we get to it. How do we compute this number? So the idea is that you take the 3 nodes after typer. So at that point, you basically have expanded all macros, right? So you have sort of the code as, well, it's seen by the Scala compiler. And it's code that is pretty much correct. You expect that after type checking, that code will likely actually compile to bytecode without errors. And you divide the number of 3 nodes after typer by the number of 3 nodes after parsing. So after parsing, the idea is that, well, that's basically the program as written by the programmer, right? So this is what we call the TPNF. And the idea is that, well, ideally, there shouldn't be much of a difference between the two, or at least that's usually what you expect. You expect something that should be around, well, 1, something closer to 1, right? Well, and then if suddenly you see that there is an explosion, so something that maybe is 5 for a specific source file, it's actually the code after typer is 5 times more than the code after parsing, well, that's going to direct your attention, right? You'll see, well, that's probably a source file where a lot of macros are happening. Maybe I have a ticking bomb in there, right? Maybe I have a lot of these type class derivations that are happening and I'm not caching. So that's why this TPNF factor, we found it useful. Of course, in Scala, there is a lot of code that may be generated during type checking. And a common example is case classes. So case classes have a companion object. The companion object has a factory method. Then in the class, you also have a copy method, and so on. So it's normal that your TPNF factor is going to be more than 1 when there are case classes in a source file, right? But the point is really, suddenly you see this factor to be like 5 times more, then you should really be looking at that source file if that was unexpected. And since we were talking about that plugin, maybe this is something that Orge could look at it and actually make it part of the plugin that is available via the Scala Center. And maybe one interesting thing is that actually it can also be lower than 1. So this might be a bit surprising. You would never expect it to be lower than 1. But that can happen if you have a lot of explicit types in your program. And because of how, well, the compiler will basically look at these explicit types and it will simplify them. So if you have a compound 3-type node, it will actually reduce it possibly to a single node. And this is the case when this TPNF factor can actually go lower than 1. But usually it's over 1, and in our experience it's around 1.2. But again, what's interesting is when it gets to be 4 or 5 times more, well, a lot of macro generation is happening during type checking, so that's what should be driving your analysis, basically. That's where you should be looking at. Then another interesting one is that the open source Scala compiler is single-threaded. And we are mentioning this, so this is number 6, because we actually see well, some people get sort of confused, or they don't expect the Scala compiler to be single-threaded. But that's actually pretty common. If you look at compilers out there, it's actually hard to find one that is multi-threaded. But what's the reason? Why is the Scala compiler single-threaded? Well, it's a batch compiler that was written over 10 years ago. And in the interest of performance, and the hardware that was available at the time, so it was a very different moment than nowadays. So the new hardware was always getting faster CPU. It was not about getting more CPUs, right? So in the interest of hardware, it actually contains a lot of mutable state. So as a consequence of that, you can see that it's not easy to parallelize the Scala compiler. And on top of this mutable state, for performance reasons, for correctness, and it also contains laziness during type checking. So really, if you put the two together, it makes it really, really hard to parallelize the Scala compiler. But there is actually one thing that has been parallelized. There is an experimental flag in 2.12.6 that allows you to parallelize generation of classifiers. So that's at the very end of the pipeline. And that is possible because all this laziness and mutability that I've described, it's over by then. So there is no more any mutability and there is no more laziness at that point. So you can actually get, let's say, some percentage speed up by parallelizing the emission of bytecode. And usually emission of bytecode is not the thing that takes the longest. Usually it's type checking. But if you're maybe a Windows user, that can actually make quite a difference because Windows is actually known to be slow at input and output. So again, it's one of these things that are easy to try. You can see if it makes any benefit. If it doesn't, you just turn it off and don't use it. So the point here is that you go and buy new hardware, but that's really not going to make any difference for you for compiling Scala. And as evidence of that, I can tell you that my colleague has a MacBook from 2017. I've got one from 2013. And in general, our performances are exactly the same when it comes to Scala compilation. So if you look at the trend in hardware, you see that there is always going to be more and more CPUs available to you. The clock is not going to grow much, right? So, well, the only thing you can do to utilize all this course is to actually have a parallel Scala compiler. And, well, as I mentioned before, there is actually one. It's called Hydra. And I'm happy to talk about it after the talk if you're interested. But if you're wondering about how fast the Scala compiler is, well, I've actually put up some number. And so we look at the line of code compiled per second. And so this is actually ignoring blank lines and comments. It's only about code. And then we look at 3 different projects. So one is the Spark code base. And so for that, I would say it's a typical code base. It doesn't use any of, I would say, the more advanced Scala features. And we see that it compiles 1,200 lines of code per second. While for a purely functional code base such as CAT, then performance actually goes down quite drastically. So we're around 480 lines of code per second. Just in comparison, I believe Java is about 10,000 lines of code per second. So yeah, you get the idea. But it's also true that so when you think about Scala code, you see 1 line of code, but in reality, during type checking, there might be 5 more or 3 more. So usually the Scala code, if you see 1 line of code, it's in reality is times 3. So it's a little bit better than actually what it looks in there. And then for play projects, it's actually interesting to see the difference between views that actually compile very, very quickly. And that actually makes sense because if you think about it, it's only about accessing models, objects, and pretty dumb logic basically inside a view, while controllers have performances that are very close to the one of cats. And the reason for that is that probably you're generating some type class for JSON serialization and deserialization. There is more complex business logic, and so it makes sense that actually we're spending a lot more time, and performances in that case, they actually goes down. And they're very similar to the one of cats. The numbers for the Spark project and cats, they were obtained from 2.12.4. I do not believe there is much of a difference between 2.12.4 and 2.12.6. Play framework, that was the Lichess project. It's still on 2.11.11. Unfortunately, it's using an old version of Play, so we couldn't test that with a Play 2, with a Scala 2.12 version. All right, now is quiz time. So we're going to see what you've learned from this presentation. And hopefully, we're also going to have some fun together. So the idea is to connect, So just connect to Kahoot.it. Sorry. Okay, let's do this. Okay. Connect to Kahoot.it. with your mobile and then enter the PIN code that you see in there. And then you can basically just hit a button and it will randomly generate a name for you. If you don't like it, I think you have up to 3 trial. And yeah, I'll just give you a couple of minutes so that everyone can join. And yeah, the first 3 basically will get a 3-month Hydra license. Just reach out to me after the talk or send me an email. I'll write down the name of the winner, so you just tell me who you are, and then you'll get the license. So people usually find it a lot of fun, so I'm actually hoping that you guys will also have fun. You'll tell me at the end. It's really going to take us something like less than 10 minutes, probably between 5 and 10 minutes. They're short and quick questions. Anyone that is still joining, or can I get it started? Yes? Oh, okay. No, there is one more person, so I'll wait another 30 seconds. Good? Yes. All right. Let's get started. Still see people joining. Yeah, yellow bunny. Good. Let's go. Okay, so who was the host country for the World Cup in 1990? Yeah, that's probably not the one that you expected as a first question. But this is so that you get used to the game, and then we can actually start with the real questions. And actually, time plays a role. So the fastest you are, the more points you get. Okay, so let's see who got it right. Yeah, probably my Italian friends got it right. Okay, so yes, it was in Italy. Good. Ready? Okay, so Fabulous Impala is leading, but it's Smart Gazelle. It's right behind him, so you should watch out. So how many instances of decoder of full name are generated in this code? Hopefully you remember the slides. Think about what happens during this type class derivation. Good. You guys are pretty good, pretty fast as well. Oh, fun. Before it was 75, now it's 77. Okay, I'll just wait 20 more seconds so that I make sure no one is excluded. Good. So yes, it's 4. Remember, there was shipping address. We actually had two instances of shipping address that had to be derived. And each of them had a full name, right? So yes, the answer is 4. Okay, Gentle Mouse is leading now, but there is a pigeon right behind him. So what was the most important new feature in Scala 2.9? That was quite a while ago. So it was new collection libraries, the parallel collections, XML literals, or triple quotes. You get bonus points if you go for triple quotes. I'm joking. So 2.9, it was actually a while ago. I believe it was in 2011. It was at the moment that TypeSafe was created. And actually, I believe that was the first release of TypeSafe. Yes, so it's the parallel collections. For the ones who thought it was the new collection library, which is actually now to be the old collection library in Scala 2.13, That was in 2.8, not in 2.9, so almost. And for the ones that actually went for triple quote, well, you know, I like you. Good, we have a new leader now. There is Space Impala. Keep it up. So how many lines of code per second does Scala-C compile in a typical project? So something not fancy, not using any of the advanced feature of the language. And yeah, probably you can tell what kind of code is that. So is it 1,200 lines of code per second, 3,000 lines of code per second? Okay. Pretty much everyone got it right. There is some people that are actually believing that Scala-C is super fast, up to 5,000 lines per code per second. That would be good. We're not quite there yet. Okay, so Space Impala is still leading it, and the Carrying Lobster is still a little bit behind him. So let's see. For same question, but now for a pure FP project. So is it 400 lines per code per second, 800 lines per code per second, 1,000 lines of code per second, or 5,000 lines per code per second? And I see someone contributing to cats actually knowing this, where it comes from, this screenshot. I think we're missing one answer. Good, yes, it's 400 lines per second, and I see there are some people having fun, probably, putting 5,000 lines per code per second. Very good. Yeah, nothing changed at the top. So which one of the following Scala features are implemented as macros? So is it string interpolations? Is it context bounds? Is it pattern matching? Or is it quasi-quotes? Yeah. Yeah, okay, I should make it shorter next time. Yes, it is quasi-quotes. String interpolation actually is not implemented with a macro. It doesn't have to. Context bound is just basically a way to describe the signature, so there is no macro involved with that. And pattern matching is actually translated into if then else, so there is again no macro in there. Oh, something changed at the top, I see. Good. So what implicit is selected? What does this program print? You can't tell it? Yeah, just take the time. I cannot make it bigger, I believe. Yeah, this is probably one of the hardest questions, also because it's hard to read. Good. So, yeah, good. A good chunk of you got it right. It's list from import because, yes, despite you had the type class in the companion object, there was also an import that utils._. And because of that, as I said at the beginning of the talk, imports have higher precedence over implicits that you put in the companion object. And so that's why list from import gets printed instead of list from companion. Okay, so Kering Lobster is leading, and now it's really going to be about speed. So for the ones that are actually behind him, you can still beat him. You just need to be very quick. So when was Scala first publicly announced? So was it in 2004, in 2006, in the future, or in 1996? And that was actually the email that was sent by Martin to announce the release of Scala. Yes, it was back in 2004. Some people said from the future. I agree, it is future technology. And who knows what happened in January 23rd, 1996? Yeah, I think I heard someone saying it. Yeah, Java happened. Yeah. Good, so let's see who is the winner. Okay, then Kering Lobster actually kept his lead. Then we have Inspired RX, and at the end, Rocky Hawk. You guys just come to me, and I'll set you up with an Hydra license. Now I'll just switch. Oh no, I don't need to do. Okay, I'll just switch back for a moment, and I'll skip the summary. But a week ago, we launched a compilation survey, a Scala compilation survey, and we'd be extremely thankful for your feedback. Actually, all this data will be made available publicly. IntelliJ also is gonna help the IntelliJ Scala team as well. It's gonna be helping the Lightband Scala team. So this is definitely something that we're gonna be happy to share. And if you didn't manage to win the 3 months Hydra license today, you can still have an opportunity by filling out the survey. We're going to give away 100 3 months Hydra licenses to people filling up the survey. Thanks, everyone, for your attention. I don't think there is any time for questions, so just grab me after the talk.
Thank you so much.